components in OSI. And actually to improve, okay, the assembly and actually changes in assembly in as SME as it is OSI. Besides having SMEs like PEMU and OSI, we also brought to the project, okay, large companies like it is Mercedes-Benz trucks. The idea is to show how SMEs can be integrated, okay, and as part of the traction or track approaches, okay, that have as subcontractors large companies like Mercedes. In this case, we'll be supporting and automating smart manufacturing environment, okay, which is linked to the digital twin approach that they are having. So we want to demonstrate how also SMEs can be integrated in the big processes of these large companies. We also have a large company in the area of construction as it is Acciona. Okay, we are doing in the construction area for supporting with robots and see special adaptations of mobile robots in the area of wall finishing in the construction area. And last and not for least, okay, we would like to, and we want to integrate robots in an area that is quite different, that is the artisan production, okay, with not taking part of the creativity and the artisan, let's say, perspective that is there, but really to support kind of repetitive work, okay, and help them to not only improve, but also to extend their craft and creativity to other areas as such. So we will are working with Oficina Keller in Naples for this approach. All of the use cases, besides having different areas, okay, they also have different challenges from the robot perspective. That means we are approaching challenges, okay, from CPS, that means for the connection and change in productions, for example, with the manipulation of the different objects, okay, that is needed through all the use cases, as well as supporting the visualization challenges. That means, okay, to have the recognition and doing 3D reconstruction of the context that involves the processes, okay, in each of the use cases. We are also supporting ergonomy and safety during the human-robot interaction, okay, as well as to see how is the best way to collaborate, okay, or do co-working with the robots and such. For this, we have been really relying in simulation tools, okay, to actually see how is the co-creation and how we can do, okay, the performance and evaluations to really set, okay, the use cases and how the robot can be used. In this contest, okay, we are finishing the first open call that we have, okay, and for this, we went through 5 challenges to actually experiment in 5 areas that technically we wanted to actually extend what was the VOJEXT approach. The first challenge was for the construction use case and development of solution designed to accomplish the plastering task, okay, and actually how the robot also will work in different manners to support construction, which is quite hard because the robot has been needed to be adapted. To this challenge, we will not present today the results as this challenge, okay, is still open, okay, and still be working in the approach, okay, as well as in the last sprints, okay, to be finished as such. So we will present the results for the other 4 challenges. Okay, one of them is navigation. This challenge has been led by Robotnik. Okay, and actually the idea of this challenge and the main aim was to develop secure and autonomous robot navigation in highly dynamic and visible environments. Okay, so the winner for this challenge was Elif Lab, and they will present the results following this presentation. Challenge 3, 4, and 5 had been led by Shadow, and actually it's been linked to the pipeline of teleoperation, and actually to support, okay, how dexterous hands like the ones produced by Shadow really can be supported in 3 areas. One in the area of visualization and actually how it can be linked, okay, with virtual reality, a headset, and actually to improve the usability of the hands and how the user can navigate around in the context, okay, using the virtual reality. Challenge 4, okay, it was to support the motion, okay, and to improve the hand mapping, using to lead motion the devices, okay, and actually how to try to do it and support it in a cost oriented manner as such, okay, and how it can be integrated in the pipeline. And challenge 5, it was to investigate in machine learning, okay, for hand mapping and see the movement to support, okay, dexterous movements as such. So this is a big summary of how VOJEXT works, how the project and the aims of the projects are, as well as how the 5 challenges have been integrated in the VOJEXT project. So now we will proceed, and I give you the floor, Luisa, okay, to proceed with the demonstrations of the challenges that we are approaching and the results that we have got from the 4 main challenges.
Okay, thank you, Xenia. So I will share my screen here because I would like to give you some overview about the acceleration program and the process. Xenia mentioned the open calls and the challenges that were being addressed. And now I'm going to give you an overview of this process. So here you can see this picture. So this journey started last year in March of 2021. So the open call, the companies started applying for the open call on F6S. So we had here some process that started with the application, and then we advanced to the evaluation of the proposals until getting to a final consensus that selected 5 companies. And then in December of 2021, we started the acceleration program, and it was divided into 3 sprints, and it lasted 6 months. So it means that the program finished in last May, and different results came, and some challenges and some issues to solve, and it was very successful. And then today we'll have the opportunity to start presenting the results. So here's just to have an overview that as mentioned, the challenge 1 is still ongoing because the duration of this challenge is a bit different from the others. So the works will continue until December. And challenge 2, navigation, that were addressed by Leaf Lab. Challenge 3 addressed by Extend Robotics, challenge 4 addressed by Tactify, and challenge 5 addressed by Code Wheel has finished in May. And I would like also to thank the partners, namely 3 that is still working with challenge 1, Robotnik with challenge 2, and the other 3 challenges were supported by Shadow Robot. So here's just it was an innovation action for sure that intended to gather innovative SMEs and to bring more challenges into the project pilots, and to also to complement the view of the partners from a technical perspective, and of course from a non-technical perspective as well, and to propose alternative scenarios and to engage cross subsectors and different technologies, and SMEs that comes from an external environment can enrich a lot the project ecosystem, and that was our intent here. Our objectives was to bring some innovative ideas, and of course during this process we faced some issues because we are dealing with some technical developments, but of course you will see this during the demonstrations. So today we'll give the floor to the companies to present the outcomes and to explain what they have been done during these 6 months. So I will give the floor here first for Extend Robotics team. They will demonstrate the challenge 3. So the floor is yours. Let me stop here sharing.
Awesome. Am I sharing? So my name is Sean. I'm the CEO and chief designer of Extend Robotics. Here we also have Bartosz, our principal engineer, also joining the call, explaining technology. You can see, you probably can't see me, but you can see me very small on a very top right corner of my camera. So we kind of set up a virtual camera here that split screens because we kind of wanted to simultaneously show quite a few things together. Yeah, so I'm sitting behind the robots to do this presentation. So bottom left should be the presentation itself. So yeah, so I'll just now start going through it. Yeah, so very quickly.
See you.
Sorry, can you see me?
Sorry, no, we cannot see you.
Can you see the split screen into 4?
Yes, we can see.
Yeah.
I think
So in one of the screen, which has the robots, and I'm the person behind the robots waving to everyone.
I think you may have to click on this stream and select pin video to have it on full screen, like the
yeah, so we can't really do like a full. So my name is Chang. So if you look for Chang Liu, Extend Robotics, you should be able to see.
So you can also, as a client, if you go to the top right and click view and then speaker view, it will show whoever's speaking. So that will show the cameras that we want to demonstrate. So in the top right, click view and then speaker view.
Yeah. Okay. Awesome. So I guess I'll start.
That works.
Awesome. So yeah, so I just start with some very high level introduction of the company itself. So so Extend Robotics, our vision is quite different from most robotic companies, which is our vision is to extend human capabilities beyond physical presence instead of replacing people. So that's why we developed this human robot interface software using virtual reality technologies to enable non-robotic experts to intuitively operate robots remotely from anywhere. We're particularly good at developing this 3D volumetric telepresence technologies that's allowing people to see remote workspace in 3D, and we believe this bring in the benefit to allow the robot operators to have accurate 3D geometry perception around the robot, which is quite important for teleoperations. Additionally, it allows the operator to have like flexible viewing angle that is independent from the camera's view, so you can dodge around the environment in 3D without the need to stuck in the camera's view. And second is that the third is to be able to remove the motion sickness, since we can reproject all the 3D shapes in 3D. So when people moves, all the computation is local, and we have very little latencies. We'll be able to show that when people moving their head around, so there's no latencies in there. Yeah.
Sorry to interrupt you, but you cannot put your presentation in full screen. Maybe.
In this settings, no. At this yeah, so kind of the streaming setup at the moment doesn't allow like a full screen. So it's one screen, yeah, one of the split screen. But with the actual slide, the slide is quite short. The main thing is the demonstration. Yeah. So now I'll hand over just to Bartosz to discuss the technology development during the projects.
Hi everybody, I am from the technical team at Extend Robotics, and let's quickly recall the challenge objectives. So it's about visualizing point cloud to improve teleoperation over two-dimensional video, and it should happen in VR in 3D and allow the user to navigate around. It should happen in real time, and it shouldn't be tied to this one solution. So it's like the compression should be, and point cloud streaming should be reusable for other scenarios. So what's difficult about it's that the raw RGB and depth data is typically exceeds 1 gigabit per second, even for a single camera, and it will quickly saturate any link. So naturally, we may use compression, but if not done correctly, it will saturate CPUs, for example. This is not a problem for RGB compression, which is major, where we can use hardware acceleration, but depth compression is actively research area, and it is quite difficult even at smaller resolutions. Another challenge is the real time, where the 3D pipeline is a lot more complex compared to the two-dimensional pipeline. There's no one single way to do it, but it also involves like the projection, UV mapping, distortion models, occlusion, handling occlusions, and 3D rendering techniques like volumetric rendering, not to mention the complexity of fusion, for example. Also, this typically happens on robotic computers with limited power. This is especially important in the context of teleoperation. And another challenge here is that the VR with navigation may cause motion sickness. And there are some other challenges here, like VR industry is currently the gaming industry centered around Windows and Android, and it is even worse than a few years ago. So we had Valve Index and, for example, Vive Pro 1, which were like working on Linux, Windows, Android, everything. And now, like the latest generations are typically Windows or Android standalone devices. So we have some opportunities here, like to fuse multiple sources in 3D for operation and to build a pipeline around the high resolution RGB and lower resolution depth, because that's the data that we can take advantage of and that typically will be present, because depth sensors are lower resolution and we may stream high resolution RGB data. Okay, Chunk, let's move on with the presentation.
Yeah.
Okay, so in terms of our development, for the compression, we have developed 3 ROS image transport. It's like FFmpeg, ZDepth, and YUV depth. And the first is hardware accelerated RGB over open hardware acceleration standard VA API. The second 2 are depth compression, like the high quality higher bandwidth and the low quality lower bandwidth, or real-time CPU for embedded SBC, single board computers. Okay, as far as the chipsets support the open acceleration standards here, so always in hardware acceleration, we are talking in the context of chipsets. As for the VR, the navigation is implemented in such a way designed to avoid motion sickness by dimming the scene while interacting. And we have decoupled the 3D model update from the rendering rate so that we can render at H head-mounted display rate, which is typically high, but update the model at data rate, which is typically the sensor rate. We have also like decoupled the ROS side and the head-mounted display side so that we can support the Linux, Windows, Android head-mounted displays in the future. In terms of visualization, we have like 2 workflows: the direct rendering workflow that works with single camera or rather which each camera independently and renders mesh with decoupled RGB and depth resolution. And we have a fusion workflow that works with multiple cameras in similar way. It's less mature but functional. And here we also have like the instant eye-to-eye calibration on request. Okay, let's move on, Cheng. And here we see, or maybe it may be difficult to see, so I will just describe. On the left side, it's like RGBD server pulling data over image transports, and it also pulls the camera info. So it's like intrinsics, the camera model and distortion model, and TF2 data. So it's like the extrinsics, so the pose between the depth and RGB sensor. On the right side is like the head-mounted display side. So we see the streaming part between the RGBD server and client, and that's where also fusion happens, and the rendering and UI it can be seen. Okay, that's all for the overview of the solution. We should proceed to the demos probably.
Okay. Yeah, thanks, Bartosz. So in terms of the demo, I just want to have an overview of what we're going to show. The objective for this demo, we have two objectives. First is to demonstrate the quality and feature of the volumetric telepresence pipeline we have developed during this project, and also demonstrating we've reached all the objectives during the project. And the second objective is to demonstrate the practical application this 3D rendering pipeline could be used in real dexterous teleoperation robots that's currently kind of collaboratively demonstrate with shadow robots. Yeah, so particularly for the demo, we have three parts. The first part, we show a single camera RGBD camera streaming that has two demos in it. That basically shows how the best possible quality we can achieve with single camera, and then we convert. Then the next step is to show the dual camera, two camera fusion algorithms pipelines, and then finally we show how this could be used in conjunction with shadow robots teleoperation system and combined together. So they will be using our 3D rendering to do teleoperations with their robots. Yeah. Okay. So yeah, so we will start now for the first demonstration. This first demo will be showing the single camera, the best quality we can achieve that's possible for this camera hardware. So basically, it's using this point cloud 3D perception that improve, obviously, a major improvement beyond 2D videos. You see things in 3D, and the really cool thing here is that we can render really high definition texture on top of the 2D renderings, on top of the 3D structure we're showing, which is the mesh. So in here we have like a 2K resolution.
Frank, may I have a suggestion? Is it possible to switch to just the single view from the VR, because when it is streamed over Zoom as 1/4, it's like degraded.
Yeah, it's not able to change configuration at the moment, because the marketing person is helping on controlling the robot at the moment. So I think what Victor can do is to zoom in to the scene, and you can already see. So you can zoom in quite severely. You can still see the text very clearly. This advantage you can see with the 2K resolution, and it's very. So we're now reaching the possibility, the maximum texture resolution possible for this camera hardware. So we're using the Kinect Azure. So additionally, you can already see that you can already interact with the environments with just the gestures pulling around. So yeah, so in this demo, it's also the background is that the bandwidth consumed by this pipeline for this setting is 100 megabits per second per camera. Yeah, so is quite useful. It's quite it's kind of the useful range that is towards a higher band. Additionally, I want to highlight that there is a shadowing problem in like any camera, so camera cannot see what's behind objects. So there you ended up having shadows behind objects. So this will be later improved with a fusion pipeline we have. So you can use two cameras. So yeah, so now if we switch to the demo 2, which is now the single camera, but under 20 megabits per second per camera constraint. So we're cutting the bandwidth into 1/5 of the previous settings. While still we can demonstrate that it's very hard to notice the difference basically with that. So this is really leveraging our compression pipeline. We have developed it that maintain the maximum amount of useful information, reduce the noise, and reduce the bandwidth severely. I cannot see. Yeah. So are we showing the second one? Yeah. Okay. Yeah. If you can zoom in and just to see probably the similar thing, but the texture is a little less sharp, but is definitely hard to notice the difference. Yeah. The texture is generally quite important for teleoperation as well. So these two demos basically demonstrate that we have met all the objectives in the development programs. And now we will switch to demo 3. That is showing the dual camera fusion algorithms. And this what we see as an initial prototype as part of the extra work we developed during the project, because we see really being able to stream things efficiently in 3D, giving us this opportunity to combine multiple camera in the most intuitive way. So people don't even need to know how many camera being there, but all the camera information being fused together into one uniformed mesh or model. So I want to highlight this is still the initial prototype. So the quality is not as high as the single camera at this stage, but we are already removing a lot of shadowings. What the guys are showing here is also we have implemented the eye-to-eye calibrations, so that we use a kind of the marker board that allows the camera to figure out their relative positions between each other, so they can overlay each other the mesh correctly.
Once you already increased the offset?
Yeah.
Yeah, it's good. Just give me a second.
So now they have finished the calibration. So used to be that they are not aligned. Now they're automatically aligned. Here now we want to show that the shadows were removed after combining two cameras together. So the two cameras are streaming from different angle around the scene. And used to be that there is a shadow behind the dog that's blocking the view of the camera to see what's on the board. But now the board can be seen. The operator can have the flexibility to view the system, the view from different angle without seeing the shadows. Yeah. Okay. Right. So the force demo here shows let's go to the force demo very quickly. So the force demo, basically we want to show that we can push the bandwidth even further by using the lossy compression. So it will compromise a little bit of the quality. However, it's still a useful system if there is a severe bandwidth limit. So now we can push them to 5 megabits per second per camera. That's basically we're still running the dual camera settings. So
it means the 3D data, so it's like the 5 megabits per second for 3D data.
So the most, yeah, exactly. So we're recalibrating, or
Yeah, done calibration.
done calibration.
Yeah.
So the fourth demo, yeah. Okay, yeah, so we just want to briefly show this because we still want some more time for actually teleoperate the robot with what we have. So the fifth demo, which is the last demo, it shows a combination of what we believe is the world's best, most dexterous teleoperation robot built by Shadow robots, and we adding our high quality single camera streaming pipeline on top of the robotic arm and robotic hand and their gloves and their control gloves to show that this is how useful this is for a real teleoperation robots. I think I'll let the guys to set up a bit.
I think they should switch to the fifth demo. Yes.
We need a little time to set up the to enable the robots as well as the cameras. The first challenge. So we're kind of brainstorming a lot of challenge. Yeah, we're showing the first one that trying to wipe the. It's kind of cleaning scenario. We want to wipe the little boxes on a table, yeah, and using robot hands together with the 3D. So you can already see that the operator can visualize the 3D workspace very well, and that gives the critical 3D information, which including the depths and shapes, colors and shapes. And we can already enable the robot arms start moving, the hands are energized, and now the operator is picking up the trolley like a real person. These demos, what used to be done by Shadow was to have a real person standing behind the robot. Oops. Oh, one of them. Oh. Oops. Yeah. Right. So. Okay. There's need some like reset.
Yeah.
Yeah, I mean, as any real demos, things are unpredictable, and I want to highlight this is very challenging. So, we're talking about, say, in this case, have each hand have 20 degrees of freedom control, and if we have two hands in operation, we have 40 degrees of freedom, just the robot hands. But on top of that, we have the two robot arm control. So that is the 12 extra degree of freedom. So in total, I would say 52 degree of freedom operations simultaneously. And just for the part of picking up the I guess it's yeah. Okay, I think it's the robotic system touching the trigger and the safety collision detections. So that needs a bit of reset. Okay. Yeah. Maybe I should just open this or-
Yeah.
Maybe not. Oh yeah, I think it's already.
Should we change that back to?
Yeah.
Okay, we'll try this.
Yeah, we'll just reset the robot arm to back to the original position.
Yeah, we.
Should we? Okay.
Also, I want to highlight this is the integration with shadow system. The integration with shadow system was taken place since yesterday, so it's like it's more like a 4 hours quick test. So so this is really outside the scope of the project, but we really want to push the limit of what's possible and utilize the project as much as possible. So this is really something that we kind of quickly do. Yeah. And it will be great if it's working well. Yeah. Yay, we're back and running. So we now have two hand.
Yeah, we are grooming it off.
Okay. So instead of doing that, we brush out grooming out the table. So that's kind of showing similar things. That was the missing part from previous demo. Awesome.
It's how the kids solve the problem also in case of mine.
Yeah, thank you.
Yay.
Yeah.
This challenge used to be very difficult for a remote operator to do.
Yeah. Oh yeah.
Yeah.
Do you want to move the camera? Yeah.
Great. Okay. Give it a go. Yeah.
Yeah. So we're bringing up a switchboard that is kind of our the demo mockups. So it's very so what we're trying to do now is to just split the very tiny fuse switches on the board. Because then currently the current so yeah, it's good. Probably need to hold a little. So it's like a real person standing there switching the fuse on and off. And this is really very difficult for a normal 2D if you're just teleoperating with normal 2D video that without 3D depth information. Yay. Awesome. We've switched all 4 or 10 switches.
Can you go for this? Triangle.
Oh, yes. Pressing buttons, flipping switches. It seems like very simple job to be done remotely now. Awesome. Yeah, so that basically marks the completion of our demonstration, and I hope everyone enjoyed and get entertained, and our robot are happy now, very happy. He's playing with his thumb. And Natasha, do you want a handshake?
Yeah. Good job, Casper.
Good job. Good job. Oh yeah. On this one.
Okay, hi.
Oh, okay.
Oh, Naka. Okay.
Awesome. So I'll hand back the mic then. Yeah.
Another thing to maybe
Oh,
highlight
anything to
is that while we see here the two-dimensional projection, the operator sees the 3D view, like each eye separately
Yeah.
in VR with like.
Any questions? Should we start answering questions, or we can leave it to the,
Oh, maybe we can move to
or
the
maybe like
challenge too.
we're using too much time. Yeah.
Yeah.
Awesome.
Okay,
Thank
but
you.
it was great. Thank you for your presentation and for the demonstration as well. Thank you very
Yeah.
much.
Awesome. Thank you.
So now we are going to move to challenge 2 with Elite Lab team. So the floor is yours.
Yes. Can you give me permission to share my screen, please?
Yes, Ana Julia, can you give
Yes.
her?
Yes. Let me find her. Okay. Okay. Yeah.
Okay. Are you able to see my screen now?
I mean, we cannot see the presentation. Oh, it's coming.
Maybe it's loading because
Yes.
something is beginning to appear, but we can still see it.
Okay. Can you see it now?
No.
Now, I suppose.
I try again. Is it appearing?
We see a blank screen, so it's like it's trying to share, but
I'm not sure why. Because it says I'm sharing my screen. Let me try this way. Now?
No, it seems it's coming.
Still the same. Maybe the good old solution like disconnecting and reconnecting to Zoom. Oh.
Yeah, probably. Yeah.
Oh yeah.
Oh, now we can see.
Okay. Okay. So thank you very much also for inviting us here today and letting us present our solution, which is called GeneZone. And we address the navigation challenge, the number 2. But I'm still having problem with my screen. Maybe I try to reconnect because it's stuck. I'm coming back in like 2 minutes. Is it okay?
Yes.
Okay, sorry for that.
So maybe we can move to challenge 3. What do you to challenge 4? What do you think, Tactic 5 team? Are you ready to present, or you would like to wait?
Yes, we are ready.
So the floor is yours. We are trying to organize here because challenge 2 is having some technical problems. So we are going to move to challenge 4 with the challenge 4 presentation. So Mosdi, thank you for your availability, and the floor is yours.
Of course, thank you so much. Thank you all for having us today and the opportunity for presenting our solution actually today. So can you see my screen?
No.
No. What about now?
Just wait a moment. We'll see if it loads or not.
Yes, we can see.
Yes, we can see it.
Thank you. Thank you. So today we're going to present the solution that we have been working on, the challenge actually I have been working on during the program, which is integrating two sensor motion. Actually, the objective of this challenge was synchronizing two lip motion devices to allow precise hand tracking and actually integrate the outputs with the teleoperation pipeline. We know all that there are various applications for the human hand tracking, but one of the and the vision-based methods and solutions are most attractive among all those recognition method. Actually, the lip motion devices controller is one of the device to track the hand position and is most interesting. But there are some shortcomings actually and challenge with this solution, which is using one sensor, is that self-occlusion and the coverage of space are two most well-known challenge with these sensors. So to overcome with this challenge, we came up with the solution of integrating two sensors. However, with this solution, actually, there are some shortcomings such as and need some settings and adjustments like the software architecture and the calibration of those sensors, both of the sensors, and also occlusion improvements. For each of these subjects, we came up with different solution. Actually, we had several experiments, and then finally chose the best performed ones among each of them. For the first one, which is a software architecture, it should be mentioned that the SDK of the sensor itself doesn't allow to have two sensors in a single machine. So we have to, well, we first we went for the two separate machines, two different laptops that have each of the sensor on them, and then most well-known solution, which is virtual machines, and then the Docker base, which is our solution with the winner actually in these methods. So with the virtual machine solutions, to have the two VMs in a single machine, or having a VM and using this host machine as well, there are some challenge with and kind of shortcomings with the first solution, which is a VM. The most important thing is that for the developers, when they want to set up packages, it's very common that dependencies issues and errors are always there. And to prevent those challenge, we try to fix settings inside Docker. In fact, this is why we went for a Docker architecture system. And also the processing times is way better in compare with the VM. So we test the two separate machines and then the VM on a single machine, and then eventually we implemented the Docker. So I saved all the settings and adjustments in the container and try to have the containers in a native Ubuntu machine. Then after this phase, we need to calibrate both of the sensors actually to with the coordinate system, matching the coordinate system of the two sensors. We needed first of all to have a flexible and adjustable workspace that have both of the sensor in it. This is why we came up with this designs actually, which used the 3D printers. So in this workspace, as you could see here, rather, we installed both sensors in the sticks and called the angles between the sensor and the stick itself B, and the angles among the two sticks A, and start to play with this architecture to find the most optimal, the position of this. And then after, we wanted to unify the data coming from these two sensors, because each of the sensors have its own coordinate system, and we need to match, first of all, both of these coordinate systems. So we fix one of the coordinate systems and then try to transform the data from the other into this actually the first one. This coordinate this matching actually can be achieved through two different methods, fully manual and also the CAPTCHA algorithm. We practices both of these methods because each of them has a pros and cons. In the first solution, which is a manual, finding the rotation matrix, minimizing the root mean square deviation between two per set of points, is that you have more freedom actually to gather the data from a different part of a space. So in that sense, the sensors can be also back to back, so it's not necessary to fix the position of the sensors. However, if you want to increase the number of the sensors, there are shortcomings there. So with the algorithm itself, we just connect these sensors and install, fix the position inside the jig, and then algorithms start to gather data from both of the sensors and repeat the process, and then try to calculate the rotation matrix and all the calculation, and come up with the best position, best angles actually. But the most challenge with this algorithm, with this method, is the higher computational time. Eventually, after that, we made sure that the position of the sensors are the best, the most optimal, and also the coordinate system is fixed. We faced with another hard problem, or in mathematics we call them multi-objective optimization problem, that we wanted to optimize or achieve two goals at the same time. So our goals is to maximize the coverage space of both of the sensors and to minimize the occlusion rate at the same time. So we call the angle between the stick and the sensor B and the angles among both of the sticks A. So we try to play with this and collect data and feed the algorithm to find the solution. So for each of the pair of these points, that's by the time we gather, feed the algorithm, and solver try to satisfy all the goals at the same times. To wrap up, after several tests, we find out that 90-degree for both of the angles is the best positions of the sensors inside the workspace. Finally, we wanted to improve the occlusion rate of the sensors and improve the performance. So in this phase, we also experiment practices 3 different methods: selection method, weighted method, and eventually Kalman filter. So in the first method, which is a selection method, each of the sensor, it's a kind of switching between the sensors. So automatically, when in presence of the noise or when one of the sensors is off, system try to follow the sensor which is active or on, and we try to demonstrate the results in presence of noise and without the noise. So in the picture 1, there is no noise in the system, and the second figure, you can see that when one of the sensors is off, in fact the lip blue is now off, and so the system try to track the sensor B. So we are losing many valuable information in this method. To improve this situation, we try to follow the weighted method to give a weight to each of the points along the way, and try to optimize these answers and piece of points actually. And eventually we applied the Kalman filter, so we could resolve the jumps when the sensors are off and on. And in this way, we could reduce the occlusion rates and have a better accuracy and have a more natural, signals in presence of noise. But the most shortcomings with this method is that the processing time is very, annoying in compared with the previous methods. We saved all these settings inside the Docker, and the Docker easily can be used by the developers to connect and integrate with the teleoperation pipeline. To show these satisfying results that we achieved, we are now going to show you some. My colleague is now available to show you, walk you through the demo. So, but we have a pre-record video in a dark space. We recorded last night because we wanted to show you that how it perform when there is when you're in a dark space. And now my colleague also is showing you how this system is working with the simulator that provided by the Shadow Robotic. Other than you, please.
Hello, thank you.
Thank you. I will show you the first. I just stopped. So this is. Can you see my screen? Yes. Okay. Here you can see 3 dockers, 1 master, and the other 2 is leap motion 1, leap motion 2, which is connected. This is the docker that we already discussed about it. So we do a calibration here. You can see the matrix, and here in the bottom, we run a launch image, which has a fusion, data fusion here. So this is how we implemented the whole system. Then we go to the robotic shadow simulation. You can see it's running right now, and then we are going to show you sorry. So it is our system.
I think you have to tilt your camera down.
Yeah. Also,
Yes.
that we cannot see the screen very well. May you please
Okay,
change? I can change it. I can change the place. Better? So you can see the boat, how it's going here and then here. So this is the live demo from a shadow simulation hand. We cannot see it very well actually because it's better. Very better because it's very the light is very annoying kinda.
Could you just maybe join the screen as a Zoom call participant, like screen sharing?
The host machine itself, can be. You can also connect through the laptop, which the simulator is on it, and then share the screen with us.
Do I have to give rise to someone to share the screen?
So this is how it's working in a live demo. So you can see again, and then you can see how it's changed. Thank you so much. Do you have any question?
Sorry, Mosley, Azadeh, your presentation is finished, or you have other videos to show?
We have pre-recorded videos because the lights in the office that you have is not very good. So if you want to see more videos from the performance of the system that we are pre-recorded last night, I can show you as well.
Okay, so maybe we can move to challenge 2. So thank you very much for your presentations and for your demonstration. And then we can move to the next challenge. Paula, are you ready?
Yeah, I hope so.
Yes.
Okay.
If it doesn't work, I can present.
Okay.
I can share my screen here.
I will try to. Okay. Is it working?
Give it some time.
Yes, it's coming.
But still nothing here apart from black screen.
Yeah, maybe I need to turn off my camera because something is like breaking. I don't know why.
Would you like me to share your presentation?
I think we are connecting with another computer, so.
Okay.
Yeah, it seems like some problem with the video. Okay.
Oh.
It
works.
Yes, we can see now.
Okay, I will try to make it bigger, but it's very slow. I think I will move to the other computer maybe. Lo condividi tu?
Yes. Can okay. We are connected with another. Okay, we are connected with another.
As there is an echo, maybe one of you will have to mute your microphone.
Okay, now it should be fine.
Yes, it's okay.
We are connected with the Elif Lab, so I think I need to have the
Ana Julia, can you
permission to show.
Can you allow the Elif Lab to present?
I already gave. Okay, let me do it again.
Yes, they are with two computers.
Okay.
Okay. Now I think you can, Gabi.
Okay, 1 second. Okay. Can you see the screen?
Yes, I can see. Yes, now it's okay.
Okay, 1 moment.
Okay, so sorry about that. And thank you again for inviting us to present our solution, which is dedicated to solving the challenge 2, navigation. I'm Paola Bonesu and one of the co-founders of Elif Lab. With me today, you saw him before, there is Gabriele, and my colleague. And we also have Lucas connected online with us today. We are in an innovative company based in Monza, and we operate in the field of data science and artificial intelligence. What we do is to develop mathematical models and algorithms to improve and automate complex processes in very different industries. Speaking about the challenge, the idea was to have a robot able to move in dynamic environments. And as you may know, dynamic environments still pose problems that are difficult to solve in order to have safe and autonomous navigation of a mobile robot. There are some issues that are challenging in this field. The first one is mapping, because we need to introduce a robot in a newer changing environment where usually we have no data or very few data already available. Localization, because we need to have a robot which is always able to localize itself. And so even when information coming from sensor is not that is not always available, we need to have a robust and reliable localization. Path planning. In order to reach our goals, we need to dynamically and efficiently calculate a path, and also to avoid obstacles during navigation, especially in dynamic environments. As you can imagine, we can have obstacles that are constantly moving, and we need to be able to avoid them even when they are not already present in the map. Perception, we need to understand how to cope with uncertain measures coming from different sensors. And also one point we wanted to address is the point related to communication, which we think is very much connected to have a safe solution, because we need to understand how the robot is making its choices, and how and to communicate these choices in a transparent way to the user. So we propose an integrated and semantic approach. So on top of what may be understood as more classical technique, we developed two abstract components. First one is a dynamic semantic reasoner. So the information coming from the robot and the information we send to the robot is represented symbolically. This means the information is easier to interpret because these are words, basically. And decisions are made on concepts. So we have, I will show you later, a dynamic graph on which we have some sort of energy quantity that allows us to generate sequences of actions. And at this stage, we also perform natural sensor fusion. So the sensor contributes with the information coming from them to construct these concepts that populate the graph. We also have a spatial graph memory, in the sense we have the 2D
metric map we construct using the information coming from sensors. But on top of that, we also have a symbolic graph map, which allows us to plot to have a faster path planning, because this map is lighter and easier to handle, and it also allows us to naturally avoid walls and other borders that may be present in the environment. This is the technical structure of our solution. You can see we have the management of information coming from different sensors. We also have this generation and selection of sequences of actions we send to the robot. This is a client-server solution. At the moment, we are also working on porting some part of this infrastructure directly on the device. So we built dedicated infrastructure from scratch, and we did this using containers and microservices. We had to make some choices, technological choices for this project. As I will show you in a moment, we used VOJEXT for creating the virtual environment, but we don't depend on this virtual environment. This solution can be plugged also to other virtual environments, or even better, to a real life situation. We have a Python client which transforms the abstract commands we send from our listener to low-level commands that help the wheels move. As said, this is a client-server structure. We adopted this MQTT broker and MQTT messages, which is similar to what happens with ROS. In ROS, you have topics where information is executed on dedicated topics. This is very similar to that kind of solution. All these services are loosely coupled, meaning that we don't need to wait for one service to be done in order to activate the other, but we have some solution in order to let the robot know that the service is active even in the absence of commands coming from the server. We also developed, I will show you them, the web interfaces for monitoring and interaction, and we chose to use Node-RED, which is a flow-based development tool, in order to simplify the flow management and development. As said, we use VOJEXT to create this virtual environment. We try to comply with some of the constraints we saw in the VOJEXT use case. So we have some industry factory-like objects. We have multiple rooms. We have some tricky points for the robot, such as small boxes, carts, desks. We also added menus. I will explain later why. But this is a complex environment to be navigated for the robot, and it poses different challenges. We also had to create a model which is based on the Robotnik Kairos, which is the mobile robot we are using in this VOJEXT project. We started from the VOJEXT model that was already available, that is the Summit XL Steel, but we integrated the sensors present on the Kairos. So we have a HD camera, 2 LiDAR sensors, a depth camera, GPS and compass, and the 4 omnidirectional motorized wheels that characterize the Robotnik. Since we didn't have the arm on the Summit X Steel, we had to add the arm on this model in order to have it more similar to the Kairos, and increase the height of the center of mass in order to have a more reliable physics. As said, we send abstract commands to the controller, and at this stage we have this Python client, which could also be a C++ client, that translates the high level into low level commands. So we send commands like straight ahead, sideways, diagonal, or turn around, and those are translated in the movement that these 4 wheels can perform. Speaking about the challenge, so we first of all addressed the mapping and localization issue. For this purpose, we tested 3 modalities. The first one is the LiDAR plus GPS using a custom algorithm developed by our team. It is also possible to use IMU or SLAM. here if GPS is only partially available, which sometimes is the case. We also tested the LiDAR plus IMU using the Breeze-Lam algorithm. So we have simultaneous localization and mapping, and we experimented with this template matching technique. I must say that all three have strengths and weaknesses, and so the choice must be guided by the use case, but having more than one allows us to be resilient when we have partial sensor problems or we don't have GPS or cases like that. Of course, GPS localization is accurate to the centimeter. SLAM localization, in this case, accuracy can vary depending on the area or other parameters, but in our test, we have localization capability around 10 centimeter. The template matching is even more accurate, but we need to test it also in other environments in order to understand its generalizability. As said, for testing purpose, we have also added additional elements in our virtual environment. One of them is manholes, because since we are using the LiDAR, we wanted to understand what happens when the robot, so the LiDAR is not parallel to the ground. So that the thing is that the LiDAR sees the floor and interprets the floor like fake obstacles. So we set up a control mechanism in this case to address this new challenge. And the control mechanism controls that the obstacle is present over time and in different positions of the robot. So we have continuity over time of these obstacles. If not, they are maybe fake obstacles. As said, on top of the 2D map we generate using a sensor during the mapping session, we create this symbolic map, which is also a memory in our system. So we have sort of a graph with landmarks similar to a triangulation, and we cover the space with this grid of known points. So we have like segments connecting these points, but as I will show you, this is good to avoid walls, but we don't need to have completely, we can also have, it is not necessary not to have obstacles in between these points, because our navigation algorithm is in any case able to avoid obstacles when navigating, because relies on another component of our system. But I will say that this memory allows, first of all, to be quicker when we generate the path when compared to the real map. Said it allows us to easily avoid the walls. Of course, since it is semantic, it's possible for the robot to communicate using information which is integrating this graph in a comprehensible manner for a human being, so text plus pictures. And it's also dynamically updatable, since during navigation, nodes can be added to this 3D, to this semantic map in order to have a better coverage of the environment. As said, an important choice in our approach is using high-level commands, because these are the commands that a human can interpret. When we understand navigation, we understand concepts like go forward or avoid the obstacle on the right or stop. So they are very much comparable to how human navigates an environment. So choices are easily communicable. Also, controller-robot communication is very light, and this also allows us to port this structure to different types of robots. We are already experimenting it with other robots, just changing the controller that adapts the abstract commands to the low-level commands that are typical to that kind of robot. As said, we have this component, which is a core component in our solution. It's a dynamic semantic graph, by means of which we generate the actions that are the sequence of actions that are sent to the robot. As you can see, the nodes in this graph are or actions or objects, and we have some sort of quantity, a sort of an energy that gives greatest impedancy to a node or another, depending on the situation and on the information coming from the from the sensors. So every 70 milliseconds, we generate a sequence. This sequence is sent to the robot in the form of an abstract command. And of course, when the robot executes this command, the energy inside this dynamic semantic graph changes. In order to trigger the navigation, we just have this interface where we double click. And once we double click on a point inside the environment, we have this trigger go to action. The path we calculate is a polyline. So we use, in this case, the A-star algorithm, but also the other algorithms can be plugged here. But this was an efficient solution in this case. So this we have this polyline, which is simplified in the form of a segment of a few points, but it is followed only as a reference, because thanks to the graph, the actual path the robot navigates depends on what is happening inside the graph I showed you before. So, okay, it needs to reach the target, but also the information about avoid obstacles or orientations or height differences is blended into the same graph. And depending on the situation, the robot can choose one solution or another. It is just, the polyline is only a reference, but in our test, we consider the goal achieved first with when the robot is far, a maximum radius far from 7 centimeters from the goal, and then 4 centimeters, and in both configuration, in 100% of times, the goals were achieved with the required accuracy. Maybe I can show you a video here just to understand what I'm talking about. Can you still see my screen?
Yes, we can.
Okay. So we have this interface, we just double click, and then the polyline is calculated. But as you can see, the robot starts receiving commands. The polyline is followed just as a reference, because as soon as the robot starts navigating, it encounters an obstacle. And the action of avoiding the obstacles, of course, is the most important here. So the robot first avoids the obstacles, then continues its navigation till the goal. We have different interfaces. So in this one, you can see commands in real time that are sent to the robot. And also in the energy part, let's say that those lab sensor, rate sensor, stimulus are like nodes in our graph. So some of the nodes are like, in this case, have more energy, and so they are used to generate the sequence of actions that is sent to the robot. So the robot here is entering another room and is approaching the target. And it reaches its goal. And in this case, when the robot stops, all the energy inside the graph is not active anymore, let's say. So, of course, as I said, achieving the goal is, of course, important, but what the challenge asked was also to correctly manage the fact that the robot can always relocate itself, even when it's forced to change its localization. It needs to be able to reach the goal, to continue navigation and reach the prefixed goal. As said, we also needed to manage the obstacles and height differences. In that case, the orientation of robot changes, so this must not affect the capability of the robot to reach the goal. And of course, the robot needs to be able to reach its goal when even when we change the final goal without having any problem. Maybe I show you another video. In this case, the robot starts the navigation, and we move an obstacle in front of the robot. This obstacle, of course, is not already present in the map, so it's a new obstacle, but nevertheless, the robot is able to avoid it. And also it goes on top of this manhole. It's able to understand the new orientation and continue navigation until it is able to reach the prefixed goal. Still, we have the commands that are sent to the controller. Another manhole, which poses a challenge, an additional challenge to the Kairos robot. And then the target is just behind this manhole. In this other video, I show you that we can, okay, the robot starts the navigation. It encounters this first obstacle. It is able to avoid it and then continues the navigation in order to reach its goal. But what if we decide to move the robot? Here is more than 1 meter from the first path we calculated in almost no time. It is able to understand where it is now, the new position, and continue navigation without any problem till the target is reached. Other obstacles here are avoided with success. And then the target is reached. So we empirically assess that we don't need to change the core of algorithm, even if the maximum or rotational speed or the acceleration of the robot may change, changing the model or changing the constraints, so that the core is stable and can function even in the very different situation. As said, we develop different web interfaces. The one we saw before is the robot status interface, where you can see the telemetry, the map, the path, live image coming from the onboard camera, the controller, and lidar information. If there is a map generated with the mapping service, it is possible to superimpose that on the lidar information. As said, you just need to double click in order to identify the target to be reached, and you have this path outline, which is planned, and then commands are sent to the robot. We also have this ITMAT interface in order to analyze historically the robot navigation session and assessing how it behaved in those sessions. We have the robot graph interface, where we can visualize the spatial memory I was telling you before, and understand how it is evolving. And we also have this symbolic graph of actions. And we have this robot monitor interface, which you also saw in the videos, where we can understand how these actions are generated in real time, understand which commands are sent to the robot. And we also have the possibility to use the camera to take snapshots in order to understand what happened during avoidance events. Speaking of performance and comparison with human operator, we took some tests here in order to understand how differently gene zone and the human operator behave. Let's keep in mind that the human operator has the complete knowledge of the environment and can see images coming from the camera, but also has the complete 3D vision of Weebots. The human operator in this case was using a gamepad with the abstract actions mapped on this gamepad. So we saw comparable timing in reaching goals, but the operator takes longer to recover maybe from errors or when it needs to go on these manholes that are tricky even for a human operator. While in comparison for Jinson, it's more difficult to avoid obstacles because it stands closer to the obstacles. But this can be improved also because we have some strange death map behavior in the synthetic environment that we expect not to have in the real environment. Also, Jinson proved to be more accurate, and also as the paths improve over time, thanks to that memory graph I showed before. And also, it was easier to manage through Jinson the lateral movement. In terms of tech performance, let's keep in mind that all this structure takes less than 200 megabytes in size, so it's very small. Everything was running smoothly, both the virtual environment and the Jinson core in the same server at 100% of speed. The highest computational cost is that of VBots, but of course, once we can try this in a real environment, we expect not to have that computational cost. And the largest data stream is that the video stream we can show in the robot status interface, but we can turn this off because the robot does not rely on that stream. Response time to an obstacle is in order of 1 heartbeat, so it's 70 milliseconds. So only sporadically we observe slightly slower response times, but everything was very, very fast. During the project, we also tried to understand the interoperability between ROS and our structure. We built a bridge in order to do that using the messaging structure I was telling you before. So we have the possibility to test also two ROS mapping and localization algorithm, the G mapping and the actors LAM. And we were able to communicate with that service, generating the needed input data, but also obtaining the correct response and the correct output via ROS topic. We also analyze the navigation algorithms, MoveBase and TAP, which are part of the ROS ecosystems. We can use the bridge and introduce them in our Jinson infrastructure. Of course, this will affect the fundamental theoretical core of Jinson, which is a semantic one, and which we think works better than those navigation algorithms. But from an infrastructural point of view, there's no problem in adapting our infrastructure in order to communicate with ROS. And this is something we are doing right now, working on the ROS integration. We especially working after the end of VOJEXT with integration with ROS2. We have developed this new bridge for ROS2, so we are able to use all the ROS services and tools without any further need for adoption. And we are introducing video analysis in this simulation using YOLO version 5. We already tested this neural network on CPU, so we are quite confident this can be introduced not only in a client server structure, but also directly on the robot. And so maybe I show you a last video about that. But the idea here is that while the robot navigates, it is able to understand what kind of objects it is facing. And the idea is to use this semantic information, introducing that into the graph, the memory, in order also to have on one side the continuity of the object during time. So once I see that chair, I don't need to, when I see that again, I know that it is that chair and not another one. And also to trigger maybe specific actions when they are related to specific objects. Maybe I need to do something with that precise box, and I have this information in my graph. So I think we are finished. So thank you very much again. I'm sorry for the technical problems we had for this presentation. Thanks.
Okay, thank you very much, Paula, for the good presentation. So last but not least, I will give the floor to Cold Wheel to address challenge 5. So Spiros, the floor is yours.
Hello, thank you. Can you hear me first up?
Yes.
Nice. Okay, let me share my screen. I would like some rights, please. Thank you so much. Right, so
yeah, yes, we can see.
We can see your screen.
nice. Okay. So hello, we're Codewheel. We're going to see some videos, some presentation about the technology and the KPIs of the project. We're going to see some videos and hopefully a live demonstration of the hand tracking part. So changing a bit the theme, we're Codewheel. We're in general focused on AI-based motion capture technologies, both in the full body, but also in the human hand. A special focus here, special focus to the markerless part, the markerless capturing of the hand motion. Codewheel is a startup founded in 2018, and we have as a mission to deliver the next generation AI-powered 3D motion capture. So that's why we submitted a proposal to the VOJEXT open call. Challenge 5, which is the hand tracking, hand mapping for the integration to teleoperation pipelines. So our case, our project here is called Real Hands. Our full title is Real-Time Markerless Hands Motion Capture. So the challenging part here is that we are using only one camera, consumer-grade camera, not a specific one, just a color camera that no markers, and we are predicting the 3D for full 3D hand articulation from just a single camera in real time. Very briefly, so the whole system is pretty simple to explain. So for every frame we get, we're using media pipe for the palm detection. This information is also provided to the end user. So the confidence or the threshold that the end user wants to use for the hand tracking is fully parameterizable. So we're using the palm detection, and we perform hand segmentation, the key point estimation to the key point estimation, and then we have the end of the pipeline has a 3D hand mesh generator with some IK involved. We provide the full hand, full 3D hand articulation as parameters. So the first part that has the media pipe as a media pipe uses a specific annotation, let's say, of its key point of its joint. You can see 21 on the right side. You can see 21 joints with specific indices, specific labeling. But for our case, for the 3D hand mesh generation, we exploit the Mano 3D mesh provided by the MPI. So it is open for research purposes. This is an R&D project. So the Mano authors provide 16 key points inside the mesh, 3D mesh, as you can see in the left image. And they provide also the 5 indices that correspond to the 5 fingertips as the 5 extra key points, 5 extra joints. So you can see here the mapping from the Mano 21 key points to the media pipe ones that are the ones that are extracted and provided to end user. To summarize some KPIs, the most critical KPIs here, the first goal was to have a real-time performance. Anything that was above 25 FPS should be acceptable for a teleoperation pipeline, and this goal has been more or less achieved with specific hardware. Moving to the second KPI here, a relatively low-cost hardware. So all you need is a laptop with a good GPU. Anything again with a 2060 or the newer generation, the 3060 and above, will do the job here. This was the second goal. The third goal was to be able to provide the joint position and orientation in real time, of course, to the end user, and of course have an acceptable angular error, which in our case was tested into in-house test set and in-house videos. So we have achieved these goals, and this is our first. These are some screenshots of what we have built. I would like to explain here before we go to the videos part. Our whole package, our whole application is packaged to a Docker and can be provided to the end user. The end user runs the Docker, and the information that he or she receives is the fingertip XYZ parameters. So the position of the fingertips and the rotations relative to the wrist, and of course the global orientation, the global translation of the wrist. You can see in the two screenshots, on the left side is the camera, the color camera feed, and on the right side is the Open 3D viewer, presenting, showcasing the generated 3D mesh and moved with specific articulation parameters. And as you can see in the right image, even having objects in your hand does not really corrupt the predictions, as there is a specific hand prior that has been learned through this machine learning pipeline, this machine learning model. Our reference was from the start. Our point of reference was the Oculus hand tracking. Of course, it's the state-of-the-art hand tracking. Facebook has integrated this software in the newest Oculus devices, Oculus Quest 2, where you can choose not to use the controllers, and there are 4 cameras at the bottom of the Oculus that are tracking your hands. And we'll see a video here. This is a video from our Oculus machine, ported in Unity. So you can see here. How we can use the Oculus and what is the state of the art here. You will recognize some specific gestures that we're going to perform later, both real time and in the videos. So here I'm playing with the Rubik's Cube or performing some specific gestures. Even Oculus in specific articulations, you can see if the hand disappears, it means that we don't have a very good tracking of the hand. Of course, it's a very stable hand, even with some instabilities in challenging poses. Yeah. So this is our point of reference. This is the first video that we used to disseminate our results first to the project. All the videos are relatively short. So you can see here, as I said, we're using an off-the-shelf camera. and we perform the 2D to 3D mapping. This is the challenging part here. Even the media pipe from Google that's providing 2D key point detections in a very robust manner. The third dimension, the depth that they're predicting, is pretty bad in specific hard articulations, and this is what we try to surpass here, and of course keep the performance in a real-time acceptable manner. So the second part is the Oculus video that I showed you earlier. So now you can see how we tested the how the media pipe palm detection threshold or confidence affects the human hand, and then we're going to see the live demo. So the green part here is when we have very good confidence. The red is when we have very low confidence. Some quick movements is just to showcase the performance in terms of the FPS. Okay, so the media pipe, the palm detection threshold is still not very clear to us. I mean, we can use, at the end of the video you can see a random mesh, right? So what's the problem here? We are predicting a 3D hand mesh, okay, specific rotations. Even if there is no hand in the field, the field of view of the camera, the regressor, the model would predict something, even this nonsense that you can see in the video right now. So the problem is that if the end user wants to actually exploit the application, we have to use a detector prior to the regressor or as a side information. So the end user will choose which threshold is best for him or her, so they can choose when not to use the articulation parameters. For example, in this last frame of the video, that there is no hand and the result is red, we shouldn't use the prediction of the regressor so we don't damage the hardware. But still, since media pipe is open up to a point in our experimentation, we've found a sweet spot, but again, it's not the best. Probably it's using any other experimenting with any other hand detector is fine, because it's a plug and play module of the pipeline. Okay, here is our contact point, and I don't want to say anything more. I would like to ask that we can pin. So I'm in the call with my phone that I want to use for showcasing the demo. It's called Spiros or Spiridon's iPhone. So if you can, I don't want to use this audio. I will use the video. If you can pin somehow the iPhones, the iPhone as a user, so you can see the video. I don't know how easy it is. Let me stop from here.
I think it may be easier if you stop sharing.
Yeah, I'm doing that now. Yeah. So stop sharing. Nice. Okay. Just give me a second. Okay, I guess that now you can see me, right? From both cameras.
Yes.
And now you can see my screen.
So I believe Julie and Casper are still working on trying to pin your iPhone view.
Okay. I think each user can even do it, by himself. But no, I think the view is acceptable, right?
In the meantime, one thing you can do as a client is if you go to gallery view and then right click and show hide non-video participants.
Sorry, come again, Ethan. Sorry.
I think now Anna Julia may have managed it. I think we're good.
Okay, good. So, okay. So we can see, as I said earlier, now we can see the view, the application without the palm detector. So in the left, window, you can see a random mesh generating. On the right side, you can see the camera feed. As you can see here, it's a pretty standard HD camera. We have experimented with more than one. So here you can see my hand. It's good, right? Okay. Okay. So this is the 3D hand prediction. Okay, you can see some specific actions here. Okay, this one, like this. Okay, this. You can see the hand. Okay. Wave, like. As you can see, it's not a metric scale, right? You can see that even if I'm touching the fingertips here of the thumb and the index, it's not the same for the 3D hand. This is a different problem here. You can see here, they're not touching because my hand and the shape that is being used, it's not the same, right? We're using we're not changing the same parameters of the mano. We're just using changing the rotations here, so the articulation of the hand. But this is a very interesting problem as a follow-up to be able to, fit arbitrary hand shapes here. We show you some extra functionality here. Something about the performance you can see here. Okay, I'm trying to grasp something. Ethan, I'm trying to do the movements that we discussed earlier, like this. Okay, so here.
Yeah, so you have better stability there than we saw with our cameras.
Yeah, I know.
Still similar problems.
Yeah, there are some problems, of course, but you can see how the camera setup changes like a lot. It's again arbitrary lighting conditions. As you can see, the camera has a random autofocus. I mean, just a commodity camera. Didn't change any parameters. Yeah, you can see how quickly I can fit the hand right here. Okay, that was from our part. A bit shorter in the presentation, but the focus here is that we can changing the camera. So here the challenging part was to go from the 2D to the 3D part, to the 3D hand articulation. Oops. Yeah, thank you, because otherwise you see the door. So the challenging part here is to be able to still perform in real time and have an accurate 3D third dimension prediction. So it's not perfect, of course, especially when you're talking about moving, operating a robot hand like the Dexter's one, which is expensive and you need perfect stability in order to not damage hardware. We had some feedback from the simulator of Dexter's hand from Shadow, which was very, very supportive in the integration. And I think this is it from our case. Thank you very much.
Okay, thank you, Spiros, for the good presentation. So we are good on time. And maybe we can move to the conclusions part, because this was the last challenge. And I will give the floor, maybe Xenia would like to start, and then I come back for the final words.
Sure. Let me share the screen. Oh, I need some some permission for sharing, please.
Okay, Ana Julia, okay. I think now you can. Xenia.
Yes, you should be able to now.
Έκανα ωραία πράγματα στο live.
Can you see my screen now?
Yes.
Okay, so in first place, I would like to thank all the open callers, okay, for all your effort and the work performed during these last 6 months, okay. And secondly, and not for less, especially all the leaders that have been supporting the open callers, like Trilogic, Shadow, and Robotnik. So actually, we thank you very much for all the effort and for integrating as the best, okay, the open callers to VOJEXT as such. As for the conclusions, okay, I just will approach the challenge that we have presented here, just to say that it has been great, and it has been a great experience. We think the results that we have from the open calls are very good, okay, and all interesting technologically from the technological perspective for VOJEXT as sure. So just to say that we really think that one of the important issues we have reached is that for all the developments, we have reached at least a near to the market stage of development. So in this case, okay, for challenge for the navigation and for the challenge 2, which was navigation in DC and dynamic environments, okay. Still, we have not been able to integrate it into the robot of Robotnik, but we have an agreement to be validated and evaluated in the robots, okay, during the project in the following months, okay. Currently, some of the robots, okay, the robots that have been produced are in the partners for the development for certain to the use cases, okay. So actually has been an issue of some resources of the robots to be sent, but for sure, okay, the next steps is to integrate challenge 2 to test it and validate it in the robots as such. As for challenge 3, 4, 5, we can say that, okay, on the visualization point of view and improving the scene and systems usability, it has been reached. It has been reached all the objectives, and we have achieved the good KPIs, okay, and even additional functionalities. And it has been fully integrated to Shadow Hands, and the integration has been very successful, as it was shown today in real time. So actually is something that we can continue to show and to promote, okay, through the DIH, I'm sorry, as also as the services, and will be done so as for during the project as such. So this is not the end, because this will continue to be part okay, of the project for all the challenges and all the open callers, okay, not only for challenge 3, to be promoted, okay, as part of the services or and with contacts and actually the name of the companies that have been part of the calls in VOJEXT. As for challenge 4, okay, we can say that it has been synchronized and actually integrated into Shadow's and teleoperation pipeline, not fully as for today. But I mean, the potential and is also there, okay. So actually it has been performed in 3 development sprints, and the scores are good, okay. And actually it has been refined for some troubleshooting, but still, you know, the full integration is there. And as for challenge 5, okay, a new method of hand mapping. This was to reproduce in machine learning the methods for hand movements and tracking. We have seen improvements, and we have seen that it really has been integrated in the sense, okay, that I'm sorry, that the control is there, okay, actually has been reached to actually get into the hand. Still some escalation is needed and some accuracy to actually put it in real life. But I mean, as for the KPIs and as for the goals of the open call, everything has been reached, okay, only some refinement as part of getting to have it fully productized is good. It works in some kind of like technology or let's say GPU processing, okay, but it's not fully scalable. However, you know, as for the open call, we think it also has been a big success. So we're very happy with the work to be done or that has been done during the open call. So actually, we thank you all very much, and we will continue to promote your work, okay, and for sure to be part of VOJEXT as such. Also, we want to say and not to forget, I'm sorry, that we are having the coming open calls and the second calls, okay? This will be for some technical and new scenarios to be added to VOJEXT, okay? So actually the aim of the new open call is to upgrade and extend VOJEXT technology to new scenarios as well as to support, okay, some of the technology that is needed, okay? That was some challenges that were left from open call 1. So please be tuned because this will be launched at the end of the year in October, November during the last trimester. So please to see so. Also, okay, this will be linked, okay, and also together with the 2 residence first artists. So those are the open calls for stars and for artists to experiment and integrate, okay, their developments and their creativity in the use cases and as for VOJEXT technology. The idea is the artists, which are also technologists, okay, will present solutions addressing specific social and technical challenges, and actually to support not only the new experimentation scenarios, but also, okay, part of the technology as such. So please be tuned for this too, because it will be launched couplet or at the same time that the second open call of VOJEXT. And as for this, okay, on my side, okay, I think we can go over the closing and to your words, Luisa. So you have the floor to conclude. And again, as part of UPM team and as the coordinator team, thank you to everybody for all the effort, and including Luisa also for the effort for having this a reality and support all the open calls as you have done it up to today. So thank you very much, as well as for the partners support. Thank you.
Okay, thanks, Senia. So I will share here my screen. One moment, please. Just for the final words. So from our side, as Senia mentioned, I don't need to complement anything or add anything because all the information were there. So now we need to work on the reports and the deliverables and the internal reports to gather all the information during the process since the beginning. So as it was mentioned, it was huge successful. So we had a lot of issues and new things came, but it's normal because it's part of an innovation environment. So thank you very much for working with us. The SMEs came into the project and brought a lot of inputs, very interesting inputs for us. And so we have a lot of work to do. So all the outcomes will be analyzed again and refined. And so we are, as Xenia mentioned, we are getting prepared to launch 2 more open calls in the next semester. So we are working on it and staying tuned for the news. So thank you very much for your time. Again, thank you for being here, and hope to see you soon. Bye-bye. So thank you very much.
Thank you.
Bye-bye. Thank you.
Bye.
Bye-bye.
Thank you. Goodbye.
Bye-bye.